Hello guys, in this video we are going to show the derivation of the isentropic relations, and as you remember we can get our change in entropy by one of these expressions. Okay, these expressions come from the integration of the Maxwell relations. This comes from, well, this one comes from okay, so the first thing that we are going to notice is that Cp and Cv both depend on the temperature or can be considered constant. So Cp and Cv, of course, are a function of temperature. And that will be called variable specific heats. Or we can assume that they are independent, they are constant. So we are going to use each one of these relations to get the relations for isentropic process using constant specific heats and then with variable specific heats. On a separate video, we're going to show the difference in analysis for both assumptions. So we're going to start with constant specific heats. So for an isentropic process, S2 minus S1 will vanish and this will be 0. Since this is 0, we can make this, and we can get all the constants to one side. Now we can flip V2 and V1 if we multiply time minus 1, and we can get the exponents on each side. So we will have, we would like to make it this relation a little bit more easier, so we are going to have this conversion. So we can rewrite this expression as remembering that R is Cp minus Cv, and remember also that K is the ratio of constant specific heats. We can convert this to K minus 1. So at the end, this relation will T2 or T1 equals. Similarly, if we start from the expression, you will get a similar expression. Again, this was for constant. Now we're going to do the same for variable specific heat. So now we are going to repeat this analysis for variable specific heats. And we are going to start from this expression. So this expression comes from this integral. Remember that from Maxwell equations we said that we're going to focus on this part only at this point of time. So this dH will be Cp, and since we have variable specific heats, it's a function of temperature times dT, everything divided by T. So when we integrate, we want to integrate this state 1 to 2, right? We can also do this as two integrals. Now, this 0, we're going to call it the state reference. This 0, we're going to call it reference state. And since it's a reference, it's arbitrary. And it's arbitrary because when we integrate, it vanishes. So this integral will leave. We can recognize that what we have on top of the numerator is heat, and heat divided by T is the definition of entropy. So we're going to call it S2 minus S1, and we're going to put this 0 on top as a superscript because we recognize that it's calculated from the reference state. Coming back then to this integral, we can substitute and say, okay, one final note, just recognize that this integral depends on the final value. So S2 and S1 with the superscript is only a function of temperature. So for our isentropic process, this vanishes, and we can solve. Now we can divide everything by R. We're going to have, and if we get the exponents and to learn, we're going to have this. Now, this top part is an argument. It's the argument of this exponential. So it's adimensional, right? And it only depends on temperature. Let me make this very clear. S2 over R, it's only a function of temperature. And the same for T1, for S1. So if we know temperature, we can get this value. And we can tabulate it. So what we are going to do is we're going to rename this variable, and we're going to do something like this. And this PR is only as a reduced pressure. It's not a pressure actually, because the number that we have on the numerator that we have on the denominator are just numbers, are dimensionless, but this PR will be a function only of temperature because it comes from here. So the exponential of this number that is only a function of temperature will be also a function of temperature. So we can tabulate. We can put the temperature and we can tabulate PR2 or PR. So for a given temperature, we're going to have only one PR1. And this will be the expression for our isentropic analysis using variable specific heats. In a new video, we are going to show how to use these two expressions. Thank you.